Hello everyone. In this lesson we're going to take a look at Newton's second law. And Newton's second law describes the relationship between force, mass, and acceleration. But before we get into that, let's talk a little bit about what each one of these terms means. Now we know a force is a push or a pull. We also know that unbalanced forces cause an object to accelerate. It makes its object change velocity. So it can speed up, slow down, or change direction. We know inertia is the property that keeps the motion the same. It keeps something doing whatever it is doing. If it's at rest, it remains at rest. If it's in motion, it stays in motion at a constant speed. You'll notice inertia does not cause a change and it is not a force. Now, how do we get mass in this? Well, mass is a measure of the amount of inertia an object has. As you guys conducted the lab, you changed the mass of the cart, and as you increase the mass of the cart, you should have noticed that its acceleration went down when a constant force acted on it. That's because the more mass an object has, the harder it is to change its motion. That is to say, the more mass an object has, the more inertia it has. So yes, mass is a measure of how much inertia an object has. It is also a measure of how much matter is in an object. So it doesn't matter where the object is. It doesn't matter if it's in a strong gravitational field or a weak gravitational field. Its mass depends on how much matter it contains. We measure mass in grams or kilograms. In the physics side of things, we usually use kilograms because of the way a newton of force is defined. A newton of force is the amount of matter, or the amount of force required to accelerate 1 kilogram of matter at 1 meter per second per second. Okay? So more mass means more inertia, and it will be more difficult to change a more massive object's motion. Okay? Which is what Newton's second law says. Newton's second law is the mathematical description of force, mass, and acceleration. Newton's second law says as mass increases, its acceleration decreases when the same amount of force is applied to it. Another way of saying that, if we use more force, then it's going to accelerate more if we keep mass the same. And we actually write this mathematically like this. Remember, that sigma, that's the symbol for sum of, or net force, it's the total force. Mass is how much matter is actually being accelerated, or what the force is acting on, and acceleration is its rate of change of velocity. You might also see this written as acceleration equals net force divided by mass. Those are the exact same equations. Okay, on this one it might be easier to see as mass increases, acceleration decreases. As net force increases, acceleration increases. But that's Newton's second law, and in a minute we'll get some example problems on how to use that to solve some problems. For now, I want to look at one more case, and that's the case of things that fall. I want to look at weight, mass, and falling objects. So when an object falls to Earth, there's two forces acting on it. I'm going to draw a picture over here. If we ignore air, then there's only one force acting on it. There's the force due to gravity. And in most cases, it's okay to ignore air resistance. For things like feathers or paper, things that have lots of surface area that catch a lot of air, then yeah, air resistance has a big effect. But for heavier, denser things, air resistance doesn't have much of an effect over short distances. So if there was no air resistance at all, the only force acting on everything is the force due to gravity, which is called weight, and that's it. That's what we call something in free fall. So we're going to ignore air resistance and we're going to explore what happens. Okay? Well, if I have two objects and one's supermassive and one's not as massive, which one is going to fall faster? Well, it is true that the weight of this object, the heavier object, is greater. It's got more mass, it's got more weight. There's a stronger attraction between it and the Earth. But it's also true that that extra weight is because it has extra mass. And we just increase the mass, which means we've increased the inertia. And if we've increased the inertia, it's harder to accelerate. So heavier objects do not fall faster than lighter objects as long as we can ignore air resistance. There's a greater force on them, but because they have more mass, they also have more inertia, and that makes it harder for them to accelerate. So on Earth, in the absence of air resistance, all objects will accelerate towards Earth at 9.8 meters per second, which is why we can use that number to calculate weight. Remember, weight is the force due to gravity. Weight equals Fg. But on this picture, the only force that I have is Fg, which means the net force equals Fg. And according to Newton's second law, that's mass times acceleration, but that means the force due to gravity is equal to mass times the acceleration due to gravity. That gets its own special little symbol. That symbol is g, and g equals 9.8 meters per second per second. So F equals mg, which means the weight, Fg, the force due to gravity, is equal to mass times 9.8. So if I give you the mass in kilograms, then all you have to do is multiply by 9.8 to calculate an object's weight. Now let's do a couple example problems so you can use Newton's second law to solve some problems. So here's a couple. What net force is needed to accelerate a 10 kilogram shopping cart at 3 meters per second per second? For a question like this, you're given some information. You don't have to draw a picture. For other questions, we'll see when a picture or a free body diagram is often helpful, but you always have to show work, which means pull out the information you're given. So we're given a 10 kilogram shopping cart, so we're given a mass equals 10 kilograms. We're given an acceleration. We want to accelerate this 10 kilogram shopping cart at 3 meters per second per second. So A equals 3 meters per second per second. And we're trying to find the net force, so we're looking for a net force is required. Alright, well this is easy. We write our equation. Net force is given by mass times acceleration. So we're going to take 10 times 3, which equals 30 newtons. So we need a net force of 30 newtons to accelerate that thing. Another one. A team of people work to pull a 30,000 kilogram airplane across a runway. They pull with a net force of 9,000 newtons. What is the acceleration of the airplane? So we're given net force equals 9,000 newtons. Right there. We're also given that the mass of the airplane is 30,000 kilograms, 30,000 kg. That's a very big airplane. And we're asked to find what's the acceleration. Okay? So net force equals mass times acceleration, and I'm going to put it in the numbers. So 9,000 equals 30,000 times A. And now I have to divide both sides by 30,000, and 1, 2, 3, 1, 2, 3. So I have 0.3 meters per second per second. Okay, there's my acceleration. So just because I've got to use the equation another way doesn't make this problem really that much harder. Now let's look at one more. Suppose a block is pushed across a table so it has an acceleration of 1.5 meters per second per second. It is pushed to the left with a force of 20 newtons while an 8 newton frictional force acts on it. Okay. First thing it says is to draw a picture for this problem labeling all the forces. Okay. The reason we do that is because there's more than one force acting, and when there's more than one force acting, we want to know about all of them. Okay. And a picture is the easy way to get that to happen. So a block is pushed across the table so it has an acceleration. I'm going to write that down. A equals 1.5 meters per second per second. It's pushed to the left with a force of 20 newtons, which means on my picture over here, I'm going to draw 20 newtons. But I'm not going to write net force equals 20 newtons because it's not, because there's an 8 newton frictional force acting on it. Well, if I'm trying to make it move to the left, that means friction is pulling against me 8 newtons. Now there are two other forces here. There's weight pulling down and there's the normal force pushing up. But those two things are going to cancel. They're going to balance. So I'm not going to worry about them. So first question here is, what is the net force acting on the block? Well, remember, net force is the total forces, and we get that by summing up these forces. But we have to take into account sign. And I'm going to say I have 8 newtons to the right, which is positive, plus a negative 20 newtons to the left. To the left is negative, so this equals negative 12 newtons. So my net force, now I can write that, net force equals negative 12 newtons. And if you had chosen to the left to be positive, then this could be positive 12 newtons. It doesn't matter. But we have a net force of 12 newtons to the left. And then it says, what is the mass of the block? So the last thing to find is the mass of the block. Well, how are we going to do that? Well, we do have a relationship between these three things. We know net force equals mass times acceleration. So first we use net force by summing up the forces. Now we're going to find net force by using mass times acceleration, except I know the net force is 12, the acceleration is 1.5, and the mass is unknown, so I leave it as m. Divide both sides of this by 1.5, and we get 8 kilograms. 8 kilograms of mass for this block.